Hello, my name is Pierre-Etienne Meunier and I'm going to talk today about the program size complexity of self-assembled paths, which is the conclusion of a 7 years long project with my co-authors Damien Regnault and Damien Woods. This result takes place in a field called molecular computing, whose goal is to compute using molecules, and more specifically DNA molecules. Here in this slide you can see an example technique from the field called DNA origami, where we force a long molecule to fold into a hard-coded prescribed shape. The bottom two rows show atomic force microscopy images of experimental implementations of this construction. But we can not only build hard-coded shapes, we can also try and compute with this model. Here it's another atomic force microscopy image, but this time it's of a binary counter. So here, for example, on this column on the left, there's a single dot encoding 1. On the column immediately to the right of it, there's another dot but shifted by 1 unit. It's encoding a 2. And then on the third column there's 2 dots encoding 3. This model doesn't. The way to design such constructions is slightly different from DNA origami, because here we're using independent components modeled as square tiles coming together to collectively build this counter. And these tiles have colors on their borders. They are inspired by Wang tilings, and they assemble based on the condition in these colors. In 2000, Rothman and Winfrey introduced a model to study these designs and the possibilities offered by these molecules. They call their model the abstract tile assembly model. In this model, we start from a seed assembly sigma, which is a connected assembly of one or more tiles. There's a finite number of tile types, T, and an infinite supply of each type. And there's also a temperature tau. I'm not going to talk too much about the temperature today, because our result takes place in the temperature 1 case, which is a simplified version of the model. An example run, for instance, is here, where we start from a single tile, sigma, as our seed, and then we proceed one tile at a time, and we add one tile if the colors on at least one side matches. So here these colors match, and we can even have mismatches, but it doesn't matter as long as at least one side matches. We can assemble the tile. And the question in this model, which has been open for more than 20 years now, is can we build interesting things in this restricted model of temperature 1? Can we build counters? Can we build the Turing machines that the more general model can build? Well, it turns out we can build some things. So an early algorithm that was presented by Rothman and Winfrey in this model is an algorithm to build n times n squares using 2n minus 1 tile types. And this is already more efficient than a naive solution where each tile is different, because that one will use n square tiles, n square tile types. And here we also have n square tiles, but just 2n minus 1 tile types. This algorithm works by first building a row, a hard-coded row, where all the tiles are different, and we're essentially counting using tiles. And the next step is to build columns. These columns are all independent from each other, not connected to each other, but they're all using the same tile types, which is what makes it efficient. So here, for example, we've built a 5 times 5 square using 9 different tile types. All right. So a big issue in this model is called pumping by similarity with Kleini's Carl lemma. Because in one dimension, this model is equivalent to finite automata. Indeed, if we're restricted to build assemblies in a line, then the first time we see a repeated tile type, we can pump between the two instances of this tile type, meaning that we can repeat the segment between these two infinitely many times. But the puzzling fact is that in 3 dimensions, this model simulates Turing machines. That's a surprising result by Kukfu and Schwader from 2011. But what about 2 dimensions? What can we build in 2 dimensions? Is it like in 1 dimension? Is it like in 3D? So this is the problem I'm interested in today. it turns out we can actually be quite efficient in 2 dimensions and build non-trivial assemblies, build non-trivial algorithms. So I already showed how to build squares, but one issue with squares is that they don't go very far. They use 2n-1 tile types, but their largest assembly has a Manhattan diameter of also 2n-1. So it's not, we're not gaining much. We're actually not gaining anything, and we're not even reusing tile types efficiently along the path. But in 2015, I showed that such tile reuse is actually possible by showing that for all positive epsilon, we can find a tile set whose assemblies are all of width 2 minus epsilon times the number of tile types in the tile set. And we've actually, along with Damien Regnault, we've actually improved this bound last year by finding tile sets that assemble only assemblies of size t log t. But how far can we go? Can we build assemblies of an arbitrary size? Well, this question is actually quite important if we ever are to build binary counters or Turing machines, because these two examples can go to binary counters can build assemblies of exponential size, and Turing machines can build assemblies of unbounded size. So before trying to even build such cool constructions, can we build large assemblies without running into the issue of pumping? Well, Doty, Petitz, and Summers conjectured in 2011 that actually no, we can't. And their conjecture is that if there is exactly one final assembly, then there's a distance d such that all paths exceeding that distance are pumpable. And here we prove something slightly different. We prove that for all seed assembly sigma and all ties at t, any assembly alpha of width at least 8t to the 4t plus 1 times 5 sigma plus 6 is pumpable or fragile, meaning that meaning that alpha can be blocked. But here you can notice that sigma appears in the bounds, which makes it slightly different from the conjecture from 2011, because our results considers the length of a path from the seed, as opposed to their conjecture, which was stated in terms of the length of any segment along the path. So our conjecture is slightly weaker in that sense. But we proved the general case of any number of final assemblies, whereas their conjecture was stated in the case of a single final assembly. All right, so how do we prove this? What did we do, and so how does it work? Well, we introduced a tool called shields, where our shield is a triple ijk of indices along the path p, and a triple ijk is a shield if, well, first the glue between pi and pi plus 1 and the glue between pj and pj plus 1 are of the same type. They're both visible from the south and they're pointing east. Here, visible from the south means that from that glue you can draw an infinite vertical ray to the south that doesn't intersect any other glue of the path. So here that's the case. These rays are called Li and Aj in this drawing. So the second condition is that the glue between pk and pk plus 1 is visible from the north. Similarly, it means that you can draw a ray Lk to the north from that glue that doesn't intersect any other glue of the path. And the third condition is that if we translate Lk by pj pi, that translation does not intersect p, or at least does not intersect p between I and k. So the translation is shown here, and you can see that indeed that translation doesn't intersect the path. All right. The main thing we do with these shields is we prove a lemma which we call the shield lemma, showing that if p has a shield ijk, then p is pumpable with pumping vector pipj, or else p is fragile. Which is actually a really cool conclusion for us. It's exactly the conclusion of our main theorem. It just remains to show that any long enough path must have a shield. One thing I want to insist on here is that we prove that p is pumpable with pumping vector pipj. It does not necessarily mean that the segments of P between I and J will be the segment we end up pumping. We might end up pumping in other segments, but that segment we pump will have the same pumping vector, the same repeating vector, Pi, Pj. So the way we prove this lemma is using a few different concepts I'm going to introduce now. The first important concept is the concept of a workspace. So what these shields allow us to do is to define a connected components C of the R2 plane that has no tile from the seed nor from the prefix of P and up to I. So here C is shown in gray. And we like workspaces because if we manage to pump in a workspace, we will know that P is pumpable. If we pump something in the workspace that doesn't intersect P again after the pumping starts, then we know that P is pumpable because we know that the pumping will not intersect any other tile, will not be blocked by anything. Alright, the second important concept of our proof is the notion of this path R that can grow in two different translations. The way we build this path is by taking P here on the drawing on the left. P is shown in brown, and so we take the suffix of P from J on and we translate it back to by Pj Pi here. That translation is shown in green. And now the way we build R is simply by tracing along P and the translation of P, turning right maximally whenever there's an intersection. So every time we have an opportunity to turn right, we turn right. So we're following here along this path, and here, for example, we have an opportunity to turn right, so we're turning right, and we get the path shown in red here on the drawing on the right. This path has the property, and we proved this in the paper, that it can grow in its initial translation shown here, and also translated by Pi Pj. All right. So the next thing, I'll come back to R later, but before that I want to find an initial pumpable segment, and then I'll use R to iterate to do an inductive proof on candidate segments. So I'll find later and later candidate segments until at some point one of them is actually can be repeated forever. All right, so the first step to do that is to find an initial to find the loudest tile of P, which we call the loudest tile with respect to Pi Pj. The way to do that is to draw the loudest tile of P that intersects a line row of vector Pi Pj. Here, this loudest tile is drawn as Pm0. All right. In this process we also defined a ray from that tile to the south called Lm0. And one thing we can notice, I'm not going to prove it here, but one thing we can notice is that Pm0 is also on R, and that's actually very important because it will help us define our initial candidate segments. The way to do this is by noticing that R can grow in the two different translations. I already explained that, and Pm0 is on R. So if we grow R translated by Pi Pj, the translation of Pm0 is here. And the next thing we do is we trace along R backwards until meeting P again. And we know we'll meet P at some point because that translation of R goes back all the way to Lj, to Pj, to this tile here. Okay, so the first time we intersect P, we call that tile PV0. And one thing we can notice is that this tile is on the right hand side of the ray here called Lm0. It's on this part of the plane. And that's actually an important remark, because it allows us to show that there's another tile Pu0 here, actually the translation backwards of PV0, the translation by Pj Pi of PV0, which is of the same type as PV0. And that gives us our initial pumping segment. And an important notice here is that u0 is strictly less than v0 because u0 is to the left of lm0, and we use that fact to show that u0 is strictly less than v0. That gives us our first candidate segments. So these are the main concepts of our proof: the workspace, R, and the Laus style with respect to pi, pj. The next steps of this proof is to show by induction that we start from a candidate segment u and vn. We try to pump it. If we can pump it, we're done. Or if the pumping conflicts, if the pumping maybe does not complete but conflicts with p, we're also done, because that shows p is fragile, and that's one of our possible conclusions. And else, if the pumping is blocked by something, well, that blocker gives a later segment un plus 1, vn plus 1, and we can show that un plus 1 is strictly larger than un. So ultimately we must run out of indices out of candidate segments. So we necessarily end in the case where we can either pump our candidate segment or break p, and this shows that p is pumpable or fragile. So this concludes the proof of our main lemma, the shield lemma, showing that if p has a shield ijk, then p is pumpable or fragile. We then use this lemma to show our main theorem by adding just one extra ingredient called spans. So a span is actually a pair of glues on a column. So we look at glue columns shown here as vertical lines, and a span is the pair of the lowest glue placed by p on this column and highest glue placed by p on this column. And you can notice that if we find two spans that have the same south glue, the same initial glue, then and the second span is at least as high as the first span, then this is actually a shield, because, for example, here this span here is higher than this span, and if ps and ps prime have the same type, then the first two conditions of the shield are met, because these glues are visible by definition. They have the same type, because that's what we just assumed. And the translation of a ray from this glue to the north, the translation by ps prime ps does not intersect p, or may intersect p just at the initial point, which is which is actually included in the shield lemma. So this is actually a shield. So if we ever are in that situation, well, we're done. P is pumpable or fragile. So what if not? So our core argument is that our path is really wide. It's exponentially wide. So if we find a long enough non-decreasing sequence of spans, we're done, because we can, by the pigeonhole principle, we can find two spans of the same type. Else, all long sequences are strictly decreasing, which means that the path is also actually really high, because if we can find very long sequences and they're strictly and any such sequence is strictly decreasing, it means it starts really long, really high. So in this case, we flip our argument, we rotate our argument by 90 degrees and use horizontal spans instead. And by enough combinatorics, we can prove that we get in all cases we get either a vertical span here. We can use a shield, or we use horizontal spans and we can get a rotated shield, and prove that P is also pumpable or fragile. So, as a conclusion, we've proved an absolute negative result about the model. By absolutes, I mean that it doesn't use any reduction of simulations. We show something that the model cannot do, by showing that if it tries to build large enough assemblies, then then we can also build infinite pumpable paths. So this is a strong condition on. This is a strong blocker on the road. Like if we ever were to build Turing machines in this model, then we would need to account for the fact that some final assemblies will have, because assemblies built by Turing machines are unbound in size, some assemblies will have infinite pumpable paths. The second highlight here is that we've developed a powerful tool for tile assembly called the sheet lemma, which we hope will be used in further results. But on the downside, our upper bound is still much larger than the best known lower bound, which is in t log t. Our upper bound is exponential in t. Alright, so thanks for your attention, and go read the paper.